students and researchers in all across the world. And I'm very glad to have this opportunity to present to you some of the recent advancement in service wave techniques for site characterization, geotechnical site characterization, and also for infrastructure health monitoring. And these advancements would not be possible without efforts from my students, including Dr. Wu, Dr. Tran, and student Mr. Paul, and also my colleagues, Professor Pan. So before I continue, before I really start the main topic of today, I would like to give a very short tutorial on seismic exploration. Right, so if you hit on the ground surface, can you see my, maybe I should use a pointer. Can you see my pointer?
Yes, it looks good.
Right.
I can see your
Yeah,
point.
so if you hit on the ground surface, you generate seismic wave, right? So the wave will travel spreading spherically, and when you hit a boundary, you can the wave can be reflected, and it's also reflected downwards. And if the interface, if the velocity is higher at the bottom, right? So the wave may travel. There is a certain angle of incident angle where you get the critical angle 90 degree and induce this head wave. Right, so there is a direct wave, refractive wave, and maybe you have also the head wave. And this is the body wave part. And then a lot of energy is trapped on the ground surface. So the ground surface serves as a wave guide because of this free stress air-solid interface. And there's a lot of energy trapped on the ground surface and travel as a surface wave. So when you hit on the ground surface, you see this seismogram. You see this direct wave and head wave. Right? So some head wave, some at a longer distance, travel faster and arrive earlier. And you see this refractive wave, and there's a lot of energy travel in terms of surface wave. Okay. Right. So the two most common near surface seismic methods is the seismic refraction method and surface wave method. So in seismic refraction, you hit on the ground surface and the wave travel, if we pick the first arrival time, which in the near offset is the direct wave, and the farther distance is the head wave. Okay, so on the ground surface is a strong trap energy travel as a surface wave. So when you hit vertically, you generate this PSV interference, and it's known as the Rayleigh wave. Right, so the Rayleigh waves have different frequency component. High frequency travel at a smaller wavelengths and has shorter depths of influence, and longer wavelengths has a deeper has a longer wavelengths, has a lower frequency, longer wavelengths has a deeper penetration. So the high energy you see on the seismogram is mainly the surface wave part, right? So in this surface wave, you have, if we transform, so the seismogram originally is in time and space domain. So if we transform time domain to frequency domain and the distance space into wave number, and we can convert it into phase velocity. And this is what is called dispersion spectrum. Okay, so in this dispersion spectrum, you can clearly see different frequency may travel at a different speed. Okay, so we can convert it into wavelengths and velocity, phase velocity. So different wavelengths has a different wave velocity. So basically, wavelengths is related to depths, and phase velocity is related to shear wave velocity. So surface wave method is has become a popular method to derive shear wave velocity profile. So we can fitting the theoretical model to the dispersion curve. So we get a shear wave velocity profile or shear modulus profile. And in terms of seismic refraction, we rely on this travel time curve. And if we hit at a different location, we generate many different ray paths. So we can invert like a 2D VP profile, VP profile. So this is kind of a size reflection tomography, right? So right now, surface wave is mainly like a 1D method, while seismic refraction is a powerful 2D imaging, but it does contain some limitation, right? There's a a condition where you cannot detect the hard layer over soft layer or embedded soft layer. There are a lot of studies trying to work toward surface wave profiling into 2D imaging using pseudo approach, multiple 1D survey to combine as a pseudo 2D shear wave velocity profile, or a full waveform inversion for that purpose. So before I really begin, I would like to emphasize the difference between 1D VS profile and 2D or 3D VS imaging. So in today's topic, we are mainly concerned of the surface wave. And in order to invert for the velocity profile, it's more convenient if we can assume within the survey receiver location is more or less a stratified, it's a layer medium, right? So in that case, we can get the wavelength phase velocity and we can invert into depths and shear wave velocity, right? So this illustration show you the sample volume, the sample, the depths, the influence distance in off-plane direction is also proportional to wavelength. So this is the kind of sample volume of surface wave. Although it's still 1D method, this kind of assumption is quite reasonable in many geotechnical applications. And also from this exercise, you can come up with a very good estimate of 1D shear wave velocity profile, where if you are interested in conducting like full waveform, 2D full waveform inversion, it could be a much better starting point. And so I just want to make clear that what kind of problem that we are dealing with, right, before I really start my presentation. So this is the outline of my presentation, and it consists of 5 parts. All right, the first 3 parts are really the main 3 steps in the surface wave method. The first one is the related to field testing and signal processing. And the second step is the forward modeling. And the third step is the inversion, to get the shear wave velocity profile or shear modulus profile. And I'm going to present 2 applications. One type is a general geotechnical site investigation. And the second type is more of man-made structure inspection. And in the inversion, the parameterization is not trivial in the inversion step. And also inversion uncertainty has not been covered enough. So these 2 aspects are often overlooked. So in my presentation, I'm going to emphasize on these 2 aspects. And then I think I have time. I will talk about the true full wave field consideration. So surface wave method, we really focus on the phase propagation. So the dispersion spectrum is really about phase propagation, and the wave field also contains the amplitude decay with distance. So if we separate dispersion and attenuation behavior and consider them both, we can invert for modulus, shear wave velocity, and also for damping ratio. And finally, I would like to show you some recent effort to extend the method from land survey to offshore, and also the air couple measurement. Okay, so the first part is about field testing. So surface wave method, a very well-known 2-station method, is called spectral analysis of surface wave method. So basically, you can have as less as just 2 receiver. So you hit on the ground and you receive 2 signal. So if you perform Fourier transform with respect to each signal, and you compute the phase difference. So the phase difference as a function of frequency. And after unwrapping, you get this phase shifting as a function of frequency. So the phase velocity is time frequency over spatial frequency, which is phase difference per distance, right? So you know the spacing of the receiver, and by determining the phase difference at each frequency, you get a phase velocity as a function of frequency, which is called dispersion curve. And in SASW approach, normally we consider near field effect and far field effect. So at certain source to receiver offset spacing, it's better for example, short distance better for high frequency, and longer distance is better for lower frequency. So this is how we can characterize the phase velocity of different frequency of the surface wave. And another approach, a survey approach, is to use multi-channel. So when you have a multi-channel, you can actually perform computing after Fourier transform of each seismogram. You can determine the phase angle at different location. So you get this phase angle as different offsets. So when you have a multi-channel and small receiver spacing, you can unwrapping your phase angle in the space domain, all right? So using the same equation, you get phase velocity at different frequency. So this is called dispersion curve, but actually layer medium, the traveling mode could be complicated. Like vibration in multi-story building, you can have a different vibration mode. The wave, when it's travel at the layer medium, it's also possible to have different mode. So I have a very simple illustration. So let's say there is a frequency component at 10 Hertz, and traveling at a certain, say, fundamental mode has a traveling speed of 200 meters per second. And if you have a higher mode of a phase velocity of 400 meters per second, so the wave field originally is a simple wave field. When you stack 2 modes together, you see the phase angle is distorted because there's this 2 mode superposition, right? So this is the fundamental mode, the phase angle versus offset, right? So the slope is related to phase velocity of the first mode, and this is the second mode. When the first mode have high energy, you get this phase angle oscillating along the dominant mode, okay? So if we can perform Fourier transform, not only with respect to time, but we can also, at each frequency, we can perform Fourier transform with respect to space. So we turn time to frequency and space to wave number. And the wave number has this relationship with phase velocity and frequency and temporal frequency. So this, for example, after this wave field transformation, you can clearly see this is the top figure is the time and space domain, right? And after 2D wave field transformation, you can clearly see a high energy of 10 Hertz. So this is exactly 10 Hertz. And you see these 2 peaks, right, in a different phase velocity. So using wave field transformation, multiple data, multiple receiver, enables you to perform 2D wave field transformation. And I clearly identify phase velocity of different mode when the receiver array is long enough. Right. So this is what we get if we perform a multi-channel analysis of surface wave. That means we perform a 2D wave field transformation. So originally, this is the data. And after wave field transformation, you transform into frequency domain, and then this sort of equivalent to basically a Fourier transform with respect to space offsets. you get this dispersion spectrum, right? You get this dispersion spectrum, which is frequency and phase velocity. So this is basically the full wave field in the transform domain. And in the wave field transformation in surface wave analysis, we can normalize to the amplitude of the wave. So we mainly focused on the phase angle, right? So this part is the phase information, and there's attenuation that I would also touch on at the end of my presentation. So basically, this is a preserve the full wave field feature, and originally is in the physical domain, and this is in the transform domain, right? So subsurface characterization can be based on full waveform inversion. That is, why not? Let's fit the Earth's profile, fitting the whole waveform. And this is exactly a lot of research are doing that, right? And but full waveform inversion can be quite complicated, and I will explain why is the case. And another possibility is the current practice of multi-channel MASW is to based on fitting the normal modes. So we're picking the spectral peak under some condition. Mostly the spectral peak in the dispersion spectrum corresponding to certain mode, especially the normal, the fundamental mode. So we can do a normal mode inversion to derive the velocity profile. And then it's also possible, and which is also the main topic of my presentation, is the frequency velocity spectrum. So this is called frequency velocity spectrum, is to fit in the whole frequency velocity spectrum to derive the shear wave velocity profile. So why surface wave? Why using FVS over the complete information of full wave field? Okay, so first, it's the FVS is insensitive to P wave. A surface wave is a Rayleigh wave is dominant by shear wave velocity, right? And this dispersion, this dispersion curve, and also the dispersion spectrum within Rayleigh wave frequency and phase velocity is relatively insensitive to VP and damping ratio. And the dispersion curve is quite informative, as I already shown that wavelength is related to depth, and phase velocity is very close to shear wave velocity. So the dispersion curve can give you a very good initial of what the Earth's profile looks like. And also FVS, although it's part of the full wave field, but if we can consider also the attenuation, the amplitude attenuation part, we reserve the whole wave field. And using the FVS greatly reduce the inversion nonlinearity, because when you work on full waveform inversion, because of the cycle skipping of this oscillating wave, is highly nonlinear. So there is a certain advantage of working in the transform domain. All right. So the different shear wave velocity profile, you can have a very different behavior in the dispersion spectrum. So the complexity depends on the shear wave velocity profile. So here I give you a few examples, right? So this is more of a normal profile, and this tree has a different embedded soft layer. And you can see how in certain Earth profile, higher mode may be dominant. And the lines shown in this figure are the free vibration mode, fundamental mode, and higher mode. These are all possible propagating mode, but how the surface wave actually propagate in certain mode or summation of different mode really depends on the Earth profile. And the bottom figures are converted into wavelengths and phase velocity, and this clearly they show you, higher velocity at shallow and lower velocity at certain depths, and then increasing again. All right. So basically, FVS contains rich information, almost the complete information of the full wave field, just in the transform domain. and it gives you some idea of what the Earth's profile or velocity profile looks like. All right, so that would be my first part, is the testing, is the basically the concept of surface wave testing and signal processing to get the dispersion spectrum or dispersion curve. The second part is about the forward model. The forward model, basically the dynamic response modeling of a layer medium subjected to vertical impact loading. Okay, so this is not really nothing new. Actually, geotechnical students all study Busnik solution in soil mechanics, and basically well, this is a homogeneous half space, but you could have a layer layer half space, right? But boosting solution is more of a static case, but we are interested in dynamic case. And actually, in pavement is ideal like layer medium. And in pavement, there is a falling weight differential testing, and people have worked on this a lot in terms of the forward modeling of FWD, right? And the FWD, they focus mainly on the amplitude as a function of offset, this diffraction curve, right? While wave, we concentrate more on how wave travel, the traveling speed, the phase shift, right? But the underlying physical problems are actually completely identical, right? So, so we are motivated to work on this problem. It's already a very classical one, but we want to work on this, re-examine this problem, because if we want to work on, take advantage of the full wave field, the actual dynamic response, instead of just the normal mode, fundamental mode, or high modes, we need to have a very efficient forward modeling, because if we are going to work on the inversion, a fast forward kernel would be very important, right? So basically, it's a layer medium and subjected to a vertical load, and we are going to work on the frequency domain. So this is like a loading, a harmonic loading, okay? All right, so the boundary variable problem, you have a governing equations, and what we do is, what we can do is we transform time domain into frequency domain. So we work on the frequency domain. And then horizontal, the radial direction, we use a Fourier Basel transform or Hankel transform. So basically transform horizontal axis radius into wave number, okay? So after transformation, the partial differential equation becomes an ordinary differential equation as a function of depth, only the z direction. Okay, so after that, we use a spectral element method or stiffness matrix method. That is, at each layer, we solve the differential equation, get a general solution. And we find the solution at the top and the bottom of the layer, right? We relate the displacement and traction top to and bottom, okay? So it's called stiffness matrix. So we get a stiffness metric of each layer. And then like a finite element method, we can assemble a global stiffness matrix. So this is traction at each layer interface, and this is displacement at each layer interface. So if we consider a unit load, and we're solving this matrix equation in the transform domain, we get the displacement at each interface. But we are only interested on the ground surface, because this is where we can take measurement. All right. So and I call this a green function in the transform domain. All right. So this is the solution in the transform domain, but we have to take an inverse Hankel transform back to physical domain. So Hankel transform and an inverse Hankel transform, the integral computation is very time consuming, and also if you do numerical integration, there's also need to control the resolution, accuracy, and also it's very time consuming. So we propose this Fourier Basel series. So this is basically like Fourier series versus a Fourier transform, similar to Fourier Basel series versus Fourier Basel transform. All right. So in this method, actually, is the computation is can be much faster, 2 or 3 order faster than integral. And so this will give us a solution back into physical domain. So it's a harmonic response at frequency. So if we perform analysis of many frequency, we can using Fourier series synthesis to get the synthetic waveform. So what is the dispersion curve? Dispersion curve, normal modes, is when there is no loading. Okay, so it's a free vibration mode. So we can get the possible solution, possible propagation mode. One way is to computing like stiffness matrix, determinant of stiffness matrix equal to 0. And computation of dispersion curve, there are several algorithms which can compute dispersion curve very fast. So this is why commercial software, we mostly rely on computing fundamental mode dispersion curve and to feed the experimental observed dispersion curve. All right, details can be found in this publication. In the end, I have a list of the reference and all the publication that cover in this presentation. And I think I email this, I bundle all this paper in a zip file and I can share with you. And also Professor Reddy can share with you after the webinar through the registration emails. Okay, another in addition to stiffness metrics, stiffness metric method works very well, and mostly it's quite stable. But there are certain conditions like very thick layer, and some condition where it might become unstable. So there are many propagating matrix method. A stiffness metric is relating traction at top and bottom at each layer, and disbursement at top and bottom. And a very convenient propagating, how assemble this multi-layer is the propagation matrix method, which is the displacement at the bottom, traction at the bottom, and relating to the bottom and top. And stiffness matrix is relating traction with displacement. And Professor Penn a few years ago proposed this dual variable position is to perturb this term. So we put a traction at the top, displacement at the top and traction at the bottom, and displacement at the bottom, traction at the top. This is related to the this different quantity has a different order. And by this permutation, we have proven that it's unconditionally stable. It's very stable computation. So this is an alternative. So how forward modeling work is you have a layer model, okay? And so you find the solution in the transform domain, the green function. So this is frequency and phase velocity. But this is the solution subject to a unit load, okay? And this is not a function of source receiver location, is the solution in the transform domain. And at each frequency, we perform Fourier Basel series, and we get the solution back into physical domain. So this is harmonic response, right? At each frequency, there's harmonic response with distance. And if we calculate many at certain location, we compute all the response and perform inverse Fourier transform or Fourier series synthesis, we get the waveform, okay? So, but we don't have to compute the waveform if we are working on the FVS, all right? So in the field, you measure the waveform, you take a Fourier transform back to harmonic response. And then using a wave field transformation, there are different algorithms of wave field transformation. Phase shift method is one of them, and you can also perform beamforming. So you get this FVS. And the green theoretical green function and FVS may look similar, but not exactly the same, because this is the experimental. Consider the receiver location, the response that your receiver location. And your wave field is discretized and truncated. So after this wave field transformation is a empirical green function, but they are not identical. So when we perform inversion, we actually we can compute the theoretical FVS, while in a field you take a measurement and you compute the experimental FVS. So you fit in FVS and you taken into account the actual source location, receiver location when you compute this theoretical FVS to fit the experimental one. All right. So this is how we can. I describe how to perform the forward model, and now, the forward modeling. We can skip the inverse Fourier transform and directly compute the FVS much more efficiently. And so before I go move to the next topic, I will show you the advantage of full-wave field, considering the full-wave field. For example, here you see two Earth shear wave velocity profile. And this is the dispersion spectrum of the two profile in the vertical direction and radial direction. And by the way, when we solve the full-wave model, we can compute not only vertical displacement, but also horizontal displacement. So in the future, we can consider multi-component surface wave method. All right. Most of the time, vertical dispersion spectrum and radial and horizontal dispersion spectrum looks very, very similar. All right. So you see the two profiles give you a very distinct dispersion spectrum, but their fundamental mode, all right, are very, very close. All right, so the FVS provide a much stronger constraint than the normal mode or fundamental mode. Okay, and also we have clarified quite a few misunderstanding. There's a leaky mode, right? There are several conditions. There are a few conditions where you can have a leaky mode. What is leaky mode? Leaky mode are the energy in the dispersion spectrum where there is no normal mode, right? There's a spectral peak, high energy where it's not a possible free vibration mode, and we call this this propagating mode not described by free vibration mode or normal mode, a leaky mode. Right, even a homogeneous half space, you can see some spectral energy, right? So especially in the horizontal component, there's a surface leaky mode. And when the structure like pavement, you have high velocity over lower velocity, there is a certain frequency you cannot find the roots in the dispersion equation. And so these energy are basically a apparent or pseudo Rayleigh wave, and it's not a theoretical dispersion curve roots, and it can be considered as a kind of a leaky mode. And more interestingly is when you have a high velocity contrast, at low velocity, this high phase-guided wave, and this phase-guided wave cannot be described by the free vibration mode also. So this traveling, for example, you can see this is Rayleigh wave, and this is phase-guided wave. And this can also can all be modeled very clearly in our full-wave field model. And so another, what could in the field, what could happen, and it's not uncommon, is that sometimes it go unnoticed. Sometimes you can have a mode oscillation. Oscillation, I have a misspelling here, or mode kissing. So if you have a high velocity contrast, even the green function, theoretical green function, the fundamental mode and higher mode almost kiss each other, right? So the experimental dispersion curve, you can have like a fundamental mode misinterpreted as a one fundamental mode when actually the wave behavior is transition from fundamental mode at lower frequency actually transition to first higher mode. All right, and when you have a velocity contrast, even it's not so high, but if you have a high Poisson ratio, this phase-guided wave can appear. And in the experimental dispersion curve, you can also see this mode kissing and interpret as a single fundamental mode. All right, and in the far field, the dispersion spectrum really depends on the resolution depends on your receiver. Your receiver array is long, you get a higher resolution, right? But if you have a shorter array and the spatial resolution is not so high. And also the far field, actually, in the far field, sometimes we say, oh, if we have a far offset, we get the fundamental mode. But actually, some higher mode manifest in a farther distance. So the model is works very efficiently and give as a powerful tool to study all kinds of wave behavior. So let's move to the inversion. All right. So I will start with a synthetic case. In a synthetic case where we have a simple two-layer model. So the black line is actually overlapped by the FVS inversion, the red line. This is a two-layer model. So we also, in this case, we also perform SASW effective mode inversion. All right. So and the effective mode SASW also work quite well, the green line. All right. So, but if you perform like in MSW, a lot of people are using fundamental mode inversion, right? So this is the case where there's a mode kissing. So this you cannot notice this because there is no theoretical dispersion curve behind this. And if we interpret this as a single fundamental mode, you get much overestimation of the velocity of the lower half space. Okay, so and this is another case where you have a high gradient. Right, the dispersion spectrum is quite complex. You have fundamental mode jump to higher mode, and then the low frequency actually jump back to fundamental mode. Right. So in this case, we cannot perform the two-station SSW, the phase analysis. It's quite erratic and not stable, and the inversion doesn't give us a reasonable profile. So we perform FVS inversion. Again, it performed quite well. And then the fundamental mode inversion reasonably well, but there's also some bias. Right, so the fundamental mode of the actual profile is this black curve. Okay, so the peak. So you see, sometimes the peak, depending on the geophone, the receiver array, the spectral peak can deviate from the normal mode. You can get a better estimation of normal mode if you have a very long receiver array. But sometimes you want to restrict your survey within your site area. So this is a case study we did 20 years ago or 25 years ago actually. We re-examined this data. In the past, we use only the fundamental mode inversion. All right, this is a location where during Chih-Ping earthquake, it was liquefied. So we have a project, we conduct several in situ testing and also a surface wave. So the surface wave, the geophone is only 23 meters long. We actually initially is about just 12 meter. We want to restrict within the same area, but if you have a short array, you couldn't distinguish higher mode. You couldn't separate fundamental mode from higher mode. So we have to settle with a little bit longer receiver array. And back then we only the commercial software we can only use the fundamental mode inversion, right? So this is the dispersion curve. And with the fitting, normally it's like commercial software initially that divided into 10 layers. So we invert the shear wave velocity and the fitting is quite nice. All right, so using shear wave velocity profile and also the VS shear wave velocity based liquefaction potential analysis, we can compute the factor of safety against liquefaction based on surface wave analysis. So this is the work done more than 20 years ago. And recently, because we made some new advancement and we try to work on the FVS inversion, all right? So when we do inversion, the first step is parameterize our model space, right? And then we have to find an initial model, and then we do a gradient descent type of search, local optimization to find kind of best fit, right? So in the surface area inversion, the parameterization is not trivial. Depending on how many layers you can, let's say, divide into 10 layers or just 2 layers, 3 layers, 4 layers, right? So in inversion, there is an Occam's razor, or the principle of parsimony. Is actually we don't want to overfitting, all right? So we want to find the simplest model that can explain the data reasonably well, right? So this is the different layer number and the misfit, and we find this L curve and find this would be considered as a more objective, best estimate. Right. So if we consider, normally we usually consider the maximum depth of investigation is about 1/3 of the maximum wavelength. So if we make this assumption, but we assume different layer number and consider principle of parsimony, we can find, in this case, we find 1, 2, 3, 4, 5 is a 5 layer. Okay, 5 layer already fit the dispersion spectrum very well. You see, this is the predicted one, and this is the measured one. So fit very well. And this red line is the FVS inversion. And this black curve is from the PS logging, right? It's actually fit quite well. And if we perform fundamental mode inversion, we get this blue curve versus the FVS. They are very different, right? But you see, the fundamental mode fitting is as good as what we have 20 years ago, but apparently very different profile if we consider Occam's razor. But you see, the fundamental mode, the blue profile, if you compute the dispersion spectrum, it's very different from the measured expanded dispersion spectrum, right? Okay, so we can do instead of automatically assuming the maximum depth of investigation, we can consider this is also a possible parameters of variation, right? So we assume different maximum depths of investigation, and so different depths of investigation, and then we get a different profile, right? You see the fundamental mode inversion, all these profile fit the normal mode, the fundamental mode, reasonably well, or almost the same. But if we do FVS inversion, right, different assumption, all the profile are stacked almost on each other, very, very small variation. So the FVS give you a very strong constraint, and you will end up with a pretty much similar profile. So it's much more insensitive to expert choice when it comes to inversion. Okay, so another one parameterization. So right now, the commercial software mostly is to determine the layer number and decide the maximum depths. And then these profile, we have a scheme of when you have say a 10 layer, and the shallow has a smaller layer thickness, and as you go deeper, has a larger thickness, right? So these layer thickness are fixed, right? You just invert the velocity because it makes the inverse problem more well posed, all right? So another possibility is to just predefine only the layer number, and you assign a layer number large enough to accommodate possible velocity variation. And this example using a 5 layer, all right? So the layer thickness is variable. So layer thickness and shear wave velocity are both variables. So when layer thickness are variable, the inversion problem becomes much ill-posed. It's very complex. So there's a lot of a local minimum. So we have to use some sort of a global optimization, like Markov chain Monte Carlo simulation. But this give you, also estimation of the uncertainty. All right, I will explain this in another example. So another application is the structure assessment, structure inspection. So this is pavement. So in pavement, I think the layer parameterization is important that we also keep layer thickness as unknown. Okay, so sometimes the layer thickness is important information, as important as shear wave velocity, and so different profile can have a very different dispersion spectrum. So we can perform inversion based on this. But in this case, since we are considered layer thickness are unknown, so we have to use a global optimization scheme. All right, so I'm not going to talk about the detail of this Monte Carlo, Markov-Chain Monte Carlo. So basically, it involves a random search, and we define a misfit function. And in this case, we use a normalized cross correlation. So this is when this NCC is 1, it means the two images are identical. So it's between 0 and 1, and we can consider NCC greater than, say, 95%, the profile is retained, is accepted, right? So we can perform this Markov-Chain Monte Carlo inversion, and this is a synthetic. Sorry. Okay, this is a synthetic case, all right? So we have measured dispersion spectrum, and the black line is the actual profile. The red line is inverted, right? This is a predicted spectrum. So in this case, we use 100 hertz to 2000 hertz. And these are the histogram, the variation. These are the gray lines are accepted profile, okay? And when we incorporate more higher frequency, we have smaller wavelengths, and you see the uncertainty is greatly reduced. And we have actual field example at the time we don't have accelerometer yet, so we use geophone, so give only up to 1000 hertz. And this is a field data inversion, and the inverted profile, the first layer thickness is 8 centimeter when the core give us about 7 centimeter. Not bad estimate, consider we only use frequency up to 1000 hertz, right? And so the inversion, the global search takes a lot of time. So we have also done some study using the deep learning sort of a convolution neural network. And so we have quite a few preliminary results, and the results are very, very promising and very, very exciting. So this deep learning approach will give you a very fast estimate almost in real time. And then after the deep learning inversion, we can actually continue on a fine tuning using a gradient descent type of approach. All right. So actually, this is I can actually stop here, but maybe I'll use another 5 minutes to quickly go over how this model can be extended. But before that, I would like to have a sort of a section summary. The FE inversion, we emphasize on the model parameterization and epistemic uncertainty, different model uncertainty related to different model parameterization. These are important aspects that are often overlooked. And I clearly show, I hope I clearly show the advantage of dispersion spectrum inversion, because it accounts for dynamic response of the actual receiver configuration, and it can avoid more misidentification, and it imposes more accurate and robust constraint. And many case studies also show it gives you higher depth resolution and greater depth of investigation. All right, so I think I'm almost used up my time, but I have two more topics. One is a full waveform consideration. That is, this is waveform, and after a Fourier transform, you have amplitude and phase. So right now, surface wave, we use mainly only the phase information, and we can get the dispersion spectrum. But this attenuation curve, okay, we can also get an attenuation spectrum. All right. So how can we do that? So if you have a plane wave, so the phase angle is related to wave number times distance, and the attenuation exponential decay with distance, right? So what we can do that is we take this amplitude, right? Amplitude is a in a viscoelastic material has an exponential decay with the distance. If we take the amplitude and using a power of J imaginary, right? So we turn real term into imaginary. And this is like the wave number term. So we can use the same phase shift method to get a spectrum. And after this operation, it becomes attenuation spectrum. But the attenuation is not only related to material viscoelastic, but also geometric spreading, right? Geometric damping. So even purely elastic, the wave attenuate with distance. All right. So what we can do is we can do we can divide every channel with first channel to remove source effect, and then we can remove geometric spreading. Is in the dispersion curve, dispersion spectrum inversion, we already get the shear wave velocity profile. So when you have a structure, we can perform purely elastic simulation, and by normalizing with elastic response, we end up with a term which is related to only material attenuation, right? So in this way, we can, this is a layer model, so we can simulate dispersion spectrum and attenuation spectrum. So this is an example where we have, 2-3% damping and 5% damping. All right, if we look at the 50 Hertz, right, dispersion curve are almost identical. That means the dispersion curve is insensitive to damping ratio. When attenuation curve, there is a significant difference. So we can perform dispersion dispersion. So we can perform dispersion inversion to get the shear wave velocity profile, and we can also perform the attenuation spectrum to get the damping ratio profile. So actually, we can also do this iteratively. So we can decouple, we can have the wave field transformation, we have the phase term and amplitude term, and we start with the phase, assume certain damping ratio, and get the shear wave velocity profile. Once you get a shear wave velocity profile, we perform attenuation spectrum inversion to get a damping ratio. And we use the inverted damping ratio to perform the FVS inversion again. And by doing this iteratively, we can perform a almost ideal, full wave field inversion. Okay. All right. So final topic. I don't think I have time, but basically what we have done is not only working on the onshore land survey, we extend the approach to offshore and also air couple. So yeah, so the offshore means mostly they use air gun and hydrofoam. So we have to model the explosive source, right? And so we can model this not only displacement but also acoustic wave. So we have worked on also field data. We collaborate with a French company to get the offshore data, and we do offshore inversion to get shear wave velocity profile. In this case, we also compare what they're using, fundamental mode inversion. All right, and it works very well synthetically, but also quite well in real world data. And finally, the air couple. So basically, air couple, the air in the land survey, we consider free zero stress boundary condition, but we can also, air and water are all fluid, okay, kind of fluid. So we can put the property of air, and this will give us, we can also model the pressure, the acoustic pressure. So we can model the microphone response. So with microphone, you can this air wave. So the air wave and the surface wave, leaky mode, liquid wave can be added together. But after wave field transformation, you can see the air wave and the surface wave. All right. So this can also be modeled quite nicely. And so we are now developing microphone system and try to come up with a full wave field inversion inspection tool for a efficient tool for pavement inspection. All right, so this is my final summary. Okay, so what I present is a fair, stable, semi-analytical solution for dynamic response in layer medium. And I hope I can convince you this full dispersion spectrum inversion, is very convenient, fully automated, and significantly enhances the accuracy and resolution. And this can also allows us to perform the elastic simulation to remove geometric spreading, so where we can accurately determine the attenuation spectrum. So the phase and amplitude information can be separated and analyzed. And for accurate full waveform field inversion of VS and damping ratio simultaneously. And finally, I show how this work has been extended to underwater MSW and also air couple MSW. Right. So thank you for your listening. And I would like to acknowledge the funding agency, National Science Technology Council in Taiwan, and our university, and thank our collaborator, Seism Ocean, the offshore data. Where we can study the underwater MSW. And I have this list, forward modeling, PSV, rally wave, and surface wave behavior. And we also have done some work on love wave and extended to transverse isotropic underwater air couple. And then the inversion part would be, study related to site investigation and is the study on the inversion uncertainty and pavement, right? And this the pavement deep learning, the paper is under review, and the offshore investigation is also under review. And I have compiled all this paper in a zip file, except those two papers that are still under review. And hope if you're interested, you can take a look. So I'm going to stop here. Thank you very much, and I hope I still have time to take